All right, ladies and gents, welcome to this week's Geotalks. Thank you for joining us. And thank you to CCIP Group for sponsoring the Geotalks as always. And this week we have the great pleasure of welcoming a new staff member who joined us in March of this year for the Geotalk stage, and that is Ga Voorspoed. Thank you for joining us. So a brief introduction to Karen for those of you who don't know her. She did her undergrad and master's research here in South Africa at Stellenbosch and UCT respectively, and then went to do a PhD at the University of Alberta, and thereafter took a prestigious LithoSphere postdoctoral fellowship at the Gemological Institute of America and a short stint as a research fellow at the University of Alberta before joining us in February of this year. March. There we go. So welcome, it's great to have you. And Karen is here working with us as part of the new advanced mass spectrometry facility and as part of the WIGGLE, and as an instrument scientist to be managing that facility and working on some fantastic isotope systems and new research that we can do to fantastic mass spectrometry. So we look forward to hearing your talk, which I guess is based on the research you've been doing the last few years. So over to you.
Thank you very much, Grant, for the great introduction. And thank you, everybody. It's my first in-person talk in 2 years. So it's nice to have an audience to speak to. And thank you also to everybody on Zoom who's joining in. I see a few familiar names there. So thank you very much for joining. So as Grant mentioned, I'm new to Wits. So I joined Wits about a month ago. And so thank you very much to everyone for making me feel so very welcome in the last few weeks. So the research that I'll be speaking about today is work that I started a number of years ago in collaboration with De Beers and GIA and also with research in Amsterdam. It is based on diamonds here from the Kaapvaal crater from Voorspoed in the UK. And so just the opening slide, beautiful image of a diamond from Voorspoed with a beautiful orange eclogitic inclusion in the center. And how we know when these diamonds formed are that we extracted the inclusions out of these diamonds and did isotopic analyses on them to determine their age. So this, as I mentioned, this has been a big collaborative effort. So I will be talking about the Voorspoed diamonds, which is in collaboration with Michael Grace, Richard Stone, Ingrid Chin, and Gareth Davies. The Bobbejaan data and the STAR data. I'll also be talking about, and that is in collaboration with Steve Richardson, John Gurnan, Steve Shirey, Mark Schmitz, and then the STAR data as well, also Mark Schmitz and Steve Shirey. And on the right is just all the institutions that have been involved in supporting this research. So I'm going to start just with an introduction on the cratonic lithosphere, what cratons are, and where diamonds form. So cratons are portions of the Earth's crust that form during the Hadean and Archean. They have long-term stability of this ancient Archean continental crust due to the presence of a thick, depleted lithospheric mantle below it. So on the right, there's an image that's been modified from Tappert and Tappert 2011, showing the ancient continental crust, and below it is this thick lithospheric keel. And so, as mentioned on the left, this lithospheric keel is depleted compared to the more fertile peridotite in the convecting mantle or in the asthenosphere. It's also less dense, and it's also seismically fast compared to the global average seismic speeds. So the lithospheric mantle on average is 150 to 200 kilometers thick below these ancient cratons. And this is where the majority of diamonds that we see at the surface today, the majority of the diamonds that are in the trade come from the lithospheric mantle below these ancient cratons. There are also other diamonds that form much deeper in the sublithospheric mantle. I won't really be talking about those today, but just know that there are also diamonds that do occur in the sublithosphere. And then they are thought to be entrained in plumes and brought up to shallower depths to also be sampled by kimberlite eruptions. So the reason that the majority of diamonds form here in this lithospheric keel is that the lithosphere has a cool conductive geotherm compared to the surrounding convecting mantle. And that is what makes it very conducive to diamond formation. And so that is what is interesting here with the Voorspoed diamonds is these diamonds formed in relation to plume magnetism. So there was intense heating of the lithospheric mantle, which seems to initially be counterintuitive to diamond formation. And so that's something that we'll be trying to figure out is why these diamonds were forming at a period of intense heating in the lithospheric mantle. So here's just an outline of all the cratonic regions worldwide. And as I mentioned, these are defined by high S-wave speeds compared to the global average. So this is a seismic model that has been developed by Andrew Schaefer, published initially in 2013, but later elaborated and republished in Nature along with Ray Pearson. So here are that's the global averages here in the middle. And so you can see that all these cratonic regions have incredibly fast seismic wave speeds compared to this global average. So we're down here in South Africa. You can see the Kaapvaal has this seismic anomaly, but most other cratonic regions as well have these really fast seismic signatures. And so it's actually a very useful exploration tool if you do seismic tomography to identify regions of the Earth's crust that have a thick lithospheric keel below it. So what are the rocks in the cratonic lithosphere? So the main rock in the lithosphere is peridotite. And there's two main types of peridotite. One is hartsbergite, the other is leusolite. Leusolite roughly has clinopyroxene, and hartsbergite does not, even though there's that's not the official IUGS classification. But most people use the terminology as leusolite being a more fertile peridotite that does contain clinopyroxene. There is also eclogite and pyroxenite, which is a more minor component of the lithosphere, but equally important because it can tell us a lot about how the lithospheric mantle formed and stabilized. And this is because eclogite and pyroxenite has basaltic ball compositions that are often formed in the oceanic lithosphere that is then subducted and then placed into the cratonic lithosphere. So these are the main rock types in the cratonic lithosphere. And we can also see these minerals from these rocks represented in diamond inclusions. So diamond forms when fluids infiltrate either eclogite or peridotite, and then you trap the pre-existing minerals in the rock during diamond growth. And so here's just some examples of mineral inclusions in diamonds, the eclogitic minerals, anthracite, and eclogitic garnet. And then at the bottom are the peridotitic minerals, so chrome dioxide and chrome pyrope here on the left, which is more pinkish purple compared to the orange eclogitic garnet. So some terms to describe the relationship between the inclusion and the diamond are protogenetic, syngenetic, and synchronous. And this has been a huge debate among people who want to understand what a diamond age means. So protogenetic refers to an inclusion that has some lithospheric prehistory and that was trapped during diamond growth. A syngenetic inclusion would be any inclusion that crystallized from the diamond forming fluid along with the carbon. And then a synchronous inclusion is sort of a mix between the two, where you can have a pre-existing inclusion that is then incorporated into the diamond forming fluid or melt, but then co-crystallizes at the same time. So you can have a protogenetic inclusion that can still be synchronous. I also show an example here of a sulfide inclusion. And for sulfides, there's no way to know whether they are eclogitic or peridotitic prior to analyzing them on the SEM. So once you analyze the major elements of these sulfide inclusions, you can determine whether they're eclogitic or peridotitic based on their nickel content. So eclogitic inclusions would have lower nickel content, whereas peridotitic inclusions would have higher nickel content. So there's no way to determine paragenesis for sulfides prior to breaking the sulfides out, analyzing them on the SEM, and getting the major element compositions. So to determine an age, an isotopic age from minerals that are included in diamond, there's two main ways. The one is to determine a model age, and this is something you can do if you only have one inclusion. If you want to determine an isochron age, or the time of diamond formation, you need at least 3 inclusions, because 2 inclusions do not make a line. You can't draw a straight line through 2 inclusions and call that an age. So you need at least 3 inclusions in order to have the possibility to obtain an isochron age. So with an isochron age, what you're dating then is the time that the mineral was trapped from the surrounding mantle. So it was closed off from any isotopic exchange. And so what you're dating is the time of last equilibration, i.e. the time of diamond formation. With a model age, if you only have one inclusion, a model age typically refers to the time that that mineral was closed off or isolated from some bulk earth reservoir that you're referring to, whether that's chondrite or the primitive upper mantle. So really, it is the time that the mineral was isolated from the convecting mantle, which really then means that you're dating the time of lithosphere formation. In some cases, there are cases where model age can mean the time of diamond formation. There are cases where that do exist, but for the most part, in order to determine the time of diamond formation, you need at least 3 inclusions in order to obtain an isochron age. So diamond dating was first done by Steve Richardson, who was at UCT and later at MIT. And this was published in 1984 in Nature. And he did this through garnet dating of inclusions from Kimberley, also here on the Kaapvaal craton. And so at the time, there wasn't sufficient sensitivity on the mass spec to measure low concentrations of samarium, neodymium, rubidium, and strontium. And so for these early studies, what Steve had to do was he had to composite garnets of similar major element compositions together, or similar major and trace element compositions together in order to then obtain an isochron age. So now with improvements to analytical sensitivity, single silicate inclusions can now be measured to obtain ages. And so now it's possible to break out individual inclusions out of a diamond, dissolve them, and then measure them on the mass spec. So this is a technique that has been pioneered in Gareth Davies' lab in Amsterdam. And this is largely because of the higher resistance amplifiers on the ion detectors. So on the Faraday Club circuits in the mass spec, if you have a 10 to the 13 ohm resistor, you're able to measure way smaller currents with sufficient precision, with high precision, so that you are then able to measure these low concentrations and determine an age. So here I've just shown a comparison from Jana Koenev's, I forgot to credit her here, sorry about that. So from Jana Koenev, where she showed just the difference in precision between the 10 to the 11 ohm amplifier circuits and the 10 to the 13 ohm amplifier circuits. So with the 10 to the 13 ohm resistors on the amplifier circuit, you're able to get very high precision. And so you're able to measure small ion currents from neodymium and strontium, which is very promising. And so in the lab that we're building here downstairs, we're getting in new terms that will also have these 10 to the 13 ohm amplifier circuits. And so we'll also be able to measure, I'm sure Kim is interested in this as well, we'll be able to measure really low concentrations of neodymium and strontium in garnets and other silicates, of course. So sulfide inclusions in diamonds was pioneered by Graham Pearson and Steve Shari working at DTM. And rhenium osmium has always, since the beginning, has always allowed for single sulfides to be used for dating. So in sulfides, you're measuring rhenium and osmium isotopic compositions and then determining an age. But here, we've never had to composite the inclusions together in order to measure them. And so certainly since Graham developed this technique in the mid-90s, this has been the premier way to determine diamond ages. However, now with single silicate work also becoming possible, we'll be seeing a lot more silicate work in the literature. And certainly today, I'll be talking a bit about both. So there are some ages that have been determined on silicate inclusions by Michael Gress and Gareth Davies, and then also some ages that have been determined through rhenium osmium isotopes on the sulfide inclusions. So why do all this work? Why are we actually interested in knowing how old a diamond is? And this is because globally, diamond ages and their stability is linked to regional tectonic processes. So tectonic processes that affect the lithospheric mantle then affects both diamond formation, but also their stability. So it's possible to actually destroy diamonds through heating or through certain tectonic processes. So dating the time of diamond formation, understanding diamond stability in the lithospheric mantle leads to an improved understanding of all the tectonic processes that have occurred through Earth's history. And so we want to know whether these tectonic processes, whether they make or break the cratonic lithosphere. So there's two main ways that the cratonic lithosphere can form, can stabilize. But what's interesting is that both these processes can also destroy the cratonic lithosphere. So there's examples where plume melting has actually created a lithospheric mantle or created depleted residues for a proto-cratonic root that was later then thickened and stabilized through subduction. There's examples where a lithospheric keel was formed and stabilized only through subduction. There's examples where both of these processes have destroyed or significantly thinned the cratonic lithosphere. And so that is why we're interested in these diamond studies and also studies of the lithospheric mantle, is because this leads to a better understanding of why we have continents, why the continents are unstable. Okay, so now that you have fairly firm foundation, hopefully, so now let's come here to the Kaapvaal. So the three diamond localities that I'll be talking about today. So Bobbejaan here on the western Kaapvaal Craton, then Voorspoed and Star both on the eastern Kaapvaal. So here are the results right up front, and then I'm just going to go through each of these one by one and just explain a little bit about the data and what we think it means for Kaapvaal Craton stability. So the Bobbejaan eclogitic diamonds formed around 2.9 billion years ago. And it's thought that this was at the time of collision between the Kimberley and the Witwatersrand blocks. So between the western and the eastern blocks, collision occurred here along the Colesberg lineament. Many eclogites were formed at this time and also eclogitic diamonds. Next is Voorspoed, where there's actually two different populations of diamonds, both related to plume magnetism. So the peridotitic diamonds at Ventersdorp formed around 2.7 billion years ago, related to Ventersdorp magnetism, and the 2.19 eclogitic diamonds from Voorspoed formed during Hetpoort or potentially ongeluk magnetism. So both of these populations of diamonds, different paragenesis, both formed in relation to plume magnetism. And then the star diamonds, just to the southwest of Voorspoed, formed around 1 billion years ago, thought to be related to the collision of the Macro and Tau along the southeastern margin of the Kaapvaal Craton. So first off, the 2.9 billion year eclogitic diamonds from Bobbejaan. Disclaimer, these are not actually photos of the Bobbejaan diamonds, but there are photos of eclogitic diamonds. I just didn't have good photogenic photos of the Bobbejaan diamonds to show in the presentation. So the Bobbejaan diamonds are actually sulfides, but they are eclogitic. So here's the rhenium osmium isochron that was produced by Mark Smit and Steve Shirey. So many of these inclusions, there's 9 inclusions that plot along this isochron. So it's around 2.9 billion years ago. So there's actually many other eclogitic diamond localities also in the vicinity of the Colesberg lineament that was thought to form or have ages that formed at a similar time. And so this is thought to be related to subduction of the Wits block and collision of the Wits block up against the Kimberley block, leading to partial melting and fluid infiltration into the Kimberley block and 2.9 billion year old diamond formation. So there are many 2.9 billion year old crustal ages in the region. So here's just an example. Also, I think this is a map that Mark Schmitz made from the Kruipen greenstone belt, the Kruipen granite greenstone terrain in the Western Kaapvaal on the Kimberley block. So there's many 2.9 ages here as well. So certainly there's 2.9 mode in the mantle in terms of the eclogites, some of the peridotites, but also in the crust, we see these 2.9 ages. And so just once again, here's the tectonic model. But what's interesting here with the Colesberg lineament is that the seismics don't actually show the same subduction signature. So the ages for the Kimberley block and for the Western block and the Eastern block are different, suggesting that they had a different history, but yet there's no seismic evidence for their collision at 2.9, but yet the ages suggest that. And so that's certainly something that we still need to investigate. And so then next is the 2.7 billion year old Voorspoed peridotic diamonds. So these are actually photos of the Voorspoed diamonds this time. So these are, you can see beautiful inclusions of garnet and kleine pyroxene in these diamonds. So it's the high chrome content in the kleine pyroxene and the garnet that gives these vivid colors for each. And so here's the SMND isochron for these peridotic diamonds. So there were 16 kleine pyroxenes and 12 garnets. And lo and behold, they plot along this beautiful isochron. So it's Ventersdorp age, so around 2.7 billion years ago. Let me just elaborate a little bit about what I show here on the Kaapvaal map. So the Ventersdorp supergroup here in green. So this was plume that impinged on the Kaapvaal crater, and we have massive outpouring of basaltic lava, across wide regions of the central Kaapvaal. So this massive magmatic and extrusive event, and yet we have diamonds that are forming at this exact same time. And so here's also just from Humbert, if I'm pronouncing that correctly, I apologize if I'm not, 2019, showing the main rift axis for the Ventersdorp, and then also where they think the plume impingement site was, which is actually in the eastern bushveld, really. But then the main extrusion of lava was much further to the west into the Kimberley block. And so here are the ages, and Kim showed this last week as well from Ashley Gumsley, just showing the ages of the Ventersdorp. So there's thought to be at least 3 or maybe 4 different plume impingement events in this massive Ventersdorp, in the massive Ventersdorp supergroup. So there was several different events, and our diamond ages overlap really nicely in the middle of this. So there's also evidence for rifting and magmatism preserved in the lower crustal granulites from these same kimberlites, so also from Voorspoed, but also in other kimberlites from the Free State, so Lace, Carvalais, Star. All of them have zircons and monazites with UPB ages 2.7, which all are related to ultra-high temperature metamorphism related to the Ventersdorp. And then last week, Kim gave a great introduction to the impact of the Ventersdorp on the Kaapvaal. So this is data that Kim kindly sent me. It's from her PhD thesis, showing metapelite here from the West Rand on the rim of the Ventersdorp dome that has SMND garnet ages also related to the Ventersdorp. So clearly in the upper crust, lower crust, mantle, and the diamonds, we see this massive impact of the Ventersdorp on the Kaapvaal lithospheric mantle and crust. And so here's just a little schematic showing the impact of the plume and how likely there was some mantle thinning and destruction at this time, because clearly there must have been dikes and sills so that the lavas could extrude at the surface. But yet some lithospheric mantle was preserved and enough for diamond formation. And so here we see peridotite ages from across the Kaapvaal. So this is a compilation that I took from Gray and Pearson. These are rhenium osmium TRD ages. So these are minimum ages for peridotites. So what these TRD ages mean is that you take the osmium isotopic composition of your peridotite, and you extract that back to your bulk earth reservoir of choice, chondrite or primitive upper mantle, to determine the minimum age for their extraction from the convecting mantle. So in other words, that is your approximation for the time that the lithosphere formed. And so across the Kaapvaal craton, this is a compilation from all these different localities, and I've just divided it up into the Wits block and then the Kimberley block. And we can see across both of the cratonic blocks, there is a mode in peridotite ages around Ventersdorp magmatism. So although there was basaltic lava extruding at the surface, we also have depletion of the lithospheric mantle and formation of some peridotites at the time. So it didn't completely destroy the lithosphere, but certainly caused some depletion and some formation then of the lithospheric mantle. So next up is the 2.2 diamonds from Voorspoed. So these are the eclogitic diamonds. So these ones with the beautiful orange garnets and the pale green amphocytes in them. So here's all the SMND data for the Voorspoed eclogitic diamonds. So there's a few inclusions that plot off the isochron. So we'll just discard those. But the ones that do plot on the isochron, so they are 10 garnets and 6 kind of pyroxenes that plot along this beautiful isochron around 2.2 billion years ago. These error bars for these two inclusions are pretty large. Even if I exclude them from the isochron, we get a similar age. So I just decided to include them anyway. But I did take them off to see what the influence on the age would be, and the age stayed the same. It was just the uncertainty on the age changed a bit. And so what are these diamonds related to? What was the source of either the heat or the fluid or the melt for diamond formation? So there is the Hekpoort large igneous province at 2.2. And this is from Niels Leonard that was published recently, showing where the Hekpoort basaltic lavas occur here in the Transvaal Basin. And so it extrudes across a very large region. And then there's also the Ongeluk formation in the Western Kimberley block. These used to be thought to be related to the same large igneous province, but more recent dating has shown that these are actually two different events, and that the Ongeluk is around 200 million years older, whereas the Hekpoort extruded around 2.2 billion years ago. So here are just some of the ages for Hekpoort and Ongeluk. So Ongeluk has now been dated to be around 2.4 billion years by Ashley Gumsley, and then the Hekpoort is a bit younger at 2.2. And so just showing here that there are a range of large igneous provinces impacting the lithospheric mantle of the Kaapvaal before the bushveld. So I had this discussion with Grant the other day, just saying, well, seems that a lot of people here work on the bushveld, but can we also do some work on the Ventersdorp and the Hekpoort, because there's other magmatic events that have also impacted the lithospheric mantle of the Kaapvaal, and we need to understand these in a bit more detail as well. So here's a schematic of Hekpoort magmatism, or once again showing plume impact at the base of the lithosphere, and then sills and dikes intruding into the lower and upper crust with basaltic lavas extruding at the surface. So certainly a large igneous province along a large region of the Transvaal, and then once again diamonds forming at the same time. So once again, data from Kimberly from Kim that she very kindly shared with me. And so she had these argon ages, once again from West Rand the Pelites, had a 2.1 age. So I'm just curious whether these could also be Hekpoort. So that's something to consider. I'm not saying they definitely are. I'm just saying they're a similar age, and maybe this is something that we could consider as well, because it certainly seems to correlate with the diamond ages and some of the other crustal ages that we have. So certainly I was very interested in Kim's cake last week, where she showed 2.7 ages, the 2.1, 2.2 ages, and those are exactly the same ages that we got for the Voorspoed diamonds. So to sum up for the Voorspoed diamonds, both of these diamond populations formed related to plume magnetism. So plume-related reworking of older mantle lithologies. So there's evidence from the isotopic compositions of these diamonds that the inclusions are pre-existing. So they had some prehistory in the lithospheric mantle. And this comes from the initial isotopic ratios from the isochrones. If you take the initial ratios and you calculate a model age for those, and you extract those back to bulk earth, either to depleted mantle or to the chondritic initial, then you get these very negative epsilon values, which gives ages of 2.7, 2.5, and then 3.2, 3.0. So the peridotitic diamonds formed in host rocks that are at least Archean, like 3.2 to 3 GA, so Meso-Archean in age, whereas the eclogitic diamonds formed in host rocks that are at least 2.7 to 2.5 billion years old. And what I found interesting for the eclogitic diamonds was that they are granulites of lace that have been interpreted as magmatic underplates at 2.7. And so those potentially could be the protoliths then for later diamond formation when the next plume came around. So we have one plume forming these magmatic underplates, and then the next heating with the next plume forming the diamonds at around 2.2. So my big confusion with this data is, how did the diamonds survive the heat? How did the diamonds avoid either carbonation to form carbonates or graphitization? Because that is normally what would be happening in the lithospheric mantle, the carbon-bearing lithospheric mantle that is being either heated or oxidized. And so one suggestion that I have is that the diamonds could be forming from smaller scale fluids or melts away from the main rift, main axis of the rift. So if we have the plume impinging in one place, if you're away from the main axis, you have slightly less heating and maybe smaller scale fluids that could then be related to diamond formation. And that is certainly what Sonia Olbach suggested for the Victor diamonds on the superior craton that formed also during breakup, continental breakup and magmatic events at 720. Another thing to consider with rifting is that plume impinging at the base of the cratonic lithosphere doesn't necessarily mean that you have just catastrophic destruction of the mantle at that time. Very often the plume, because the lithospheric keel is strong and depleted and dehydrated, you first need to metasomatize it and weaken it for then later destruction. So this is a model from Steve Foley showing plume impact. And then you first start off by metasomatizing the lithospheric mantle with melt channels, bringing in like water oxidizing parts of the lithospheric mantle. And so you're slowly weakening it and refertilizing it. So you're pre-weakening it, and then a later plume would then do the big job and destroy parts of the lithospheric mantle. Another option for diamond formation related to rifting is that you had asymmetric rifting. And so once again, I'm showing this plot where it's thought that the main plume impingement site is in the eastern bushveld, but that the rift axis and the extrusion of the basaltic lavas was here in the western Kaapvaal. And so it could be a scenario where you had your main plume impact here, and then you have your main extension occurring way off axis. And this could be a scenario where you can then extensively heat the lower crust in one area, but maintain a thick lithospheric mantle with diamonds in a different area of the Kaapvaal. And so I'm just going to end off with the star diamonds. So these are peridotitic diamonds to the southwest of Voorspoed. And so these are not related or to any plumes, but to collision along the southeastern margin of the Kaapvaal. But strangely enough, these are peridotitic diamonds that are related to collision and subduction. And in the previous case of Voorspoed, we had eclogitic diamonds related to a plume. So it is a little bit counterintuitive because you would normally expect eclogitic diamonds to only be associated with collision and the peridotitic diamonds then to potentially be associated with a plume. So once again, here's the rhenium-osmium data for star, and there are 7 sulfide inclusions that plot along an isochron around 1 GA. So there is some detail here that Mark and I are working out, but the majority of the inclusions plot along an isochron of around 1 GA. What is interesting here is that the initial ratio from this isochron is very radiogenic compared to a bulk earth reservoir. In this case, I'm just plotting up chondrite. So here are the Bourboulon eclogitic diamonds that have an enriched initial ratio, an elevated initial ratio compared to bulk earth at 2.9. And here are the star diamonds that also have an enriched initial ratio compared to bulk earth reservoir relative to chondrite. And so it is this elevated ratio and also the timing overlap that leads us to conclude that these diamonds formed in association with subduction and collision along the margin of the Kaapvaal craton. There's also other 1 billion-year-old diamonds in the southern Kaapvaal from Koffiefontein and from Jacobsfontein. Sonja Albach, Graham Pearson, both have diamond ages from these localities that have a similar age to the diamonds at Star. And so there are 2 sort of tectonic events that are happening in the Kaapvaal at this time. The one is plume magnetism, the Mkhonto plume at around this time. This is just a plot from New Ashwell. And then, as I mentioned, collision along the southeastern margin of the Kaapvaal craton, also around this time. Thought to start around 1.35 and ending around potentially around 1.1 and later. So diamond formation is closely temporally related to subduction and collision along the southeastern margin of the Kaapvaal. And so this shows that there was fluid mobilization into the more central parts of the craton as well. The reworking of the subduction zone wasn't restricted to the margin of the craton. And so just to go back here to the enriched initial ratio, this is what leads us to conclude that it potentially wasn't the Mkhonto plume that caused diamond formation, but rather that it was in Macmillan-Tower subduction collision. Is because we need an enriched isotopic composition, which we can only get in a reservoir that had long-term isolation from the convecting mantle, and that would be the oceanic lithosphere. It's enriched in rhenium, so you can have long-term ingrowth of radiogenic osmium, and then fluids originating from that basalt in the subducting slab could then infiltrate into the Kaapvaal cratonic lithosphere and form these diamonds that have the sulfides with the enriched initial ratio. And so just ending off with a slide again, just showing the range of ages that we now have for these diamonds. So documenting around 2 billion years of lithosphere evolution across the Kaapvaal craton. So the eclogitic diamonds forming as a result of collision, but then we also have eclogitic diamonds forming as a result of plume magnetism. And then the same with the peridotitic diamonds. So I think this really reinforces that many inclusions in diamonds are pre-existing and that the fluids are simply infiltrating into the host rock and then trapping those inclusions during growth. And so here is just an overview then of all the published diamond isochron ages from the Kaapvaal craton. And so I have split that up into the different terrains. And you can see how very often these diamond ages relate to key tectonomagmatic events in the lithosphere mantle. So certainly here's Ventersdorp, we have the Voorspoed diamonds, but also you could see how overpopulated the Kimberley block and the Zim craton margin are with eclogitic diamonds. They certainly are more common, and so it really emphasizes the role of subduction in refertilizing the lithospheric mantle and making the Kimberley block and other parts of Southern Africa so productive for diamonds. What this also emphasizes is that cratons do not necessarily have to be stable since the Archean. So this has been the prevailing definition for a craton, is that they are, that a craton has been stable since at least 2.5. But all these diamond ages clearly show that the cratonic lithosphere can see continual reworking even after the Archean into the Proterozoic as well. And so there is now a new definition for the craton, and that is because, sorry, it just advanced a little bit too fast for me. So there is a new working definition for craton, and that is based on the fact that the thickest lithosphere is not exclusive to the oldest crust. So there's many examples globally from seismics where you have fast seismic wave speeds underlain by thick lithospheric mantle, 150, 200 kilometers, but you have Proterozoic crust. And so a new working definition is that you had to have stability for at least 1 billion years, but at least have a very thick lithospheric keel that promotes stability of this craton. And so we think that this definition works really well for the Kaapvaal because the diamond ages show that the craton has experienced repeated episodes of reworking. And now I'm just waiting to, there we go. So there are lots of cratons that still have undated diamonds. So here's a map of the world. All the red areas are cratons that have diamond ages. And all the black are cratonic regions that have diamonds, but we have no idea how old they are. And so there's still a lot of work to do because, as I hope I've convinced you, that diamond dating and the correlation of these diamond ages and diamond stability with tectonic events leads to an improved understanding of the processes that can form and destroy cratons. And here's just showing how sparse the global craton diamond age record is compared to Southern Africa, where the Kaapvaal and Zimbabwe cratons have numerous more diamond ages that have been published. So certainly a lot more work to do. And so I'll leave you there, and hopefully you guys have some questions. Thank you.
Any questions from the audience here? See there's some chat.
So we're having some sound issues.
Yeah.
Oh no.
Never sound.
Oh no.
I
Oh,
checked.
okay.
It's
Like just spoke for an hour and no one heard a thing I said.
they heard you. They
Okay.
heard you.
Okay.
Okay. We have a first question from Sarah. If we can just speak loudly so the Zoom audience can hear you.
Sure. So, Karen, are these all diamond middle separate, or were any of them in situ diamonds? Because then potentially you could look at your temperature deficit by calculating the temperature from the peridotype that you found them, or the ectotype that you found them, or they're all just separate.
Unfortunately, these were all diamonds. They were not in situ in the host rocks. That would be ideal. The ideal scenario for people who don't study diamonds like Sarah and I is if you had the diamonds still contained in the host rock, because then you can study the post assemblage, study the diamonds as well, maybe get an age from the host rock from the Asymmetric and the Titan Sumerian and the garnets, and then study the diamonds and the inclusions. However, those samples are not as common as we would hope. So, yeah, unfortunately, no, but thank you so much and stuff.
Okay, so some comments here. Thank you for the great talk.
Oh, thanks, Hannah. Thanks, Finus.
And let's just make sure everyone can unmute themselves. Are there any questions from the audience online? You can raise your hand or you can simply unmute. Any more from the room here? Yes, Ben.
Thanks,
Okay.
Cara. I really enjoyed your talk.
Thanks.
The origin of the inclusions themselves, the silicates inclusions, have they formed at the time of plume magnetism? Is that new lithosphere that's forming back inside? What is the origin of the?
Yeah, so, well, the ages that we're getting from the inclusions are the time of plume magnetism. And so that is the time of last equilibration. However, we know that the inclusions were pre-existing. So let me just, now you've ruined the thing here. How do I go back?
Just try the arrows.
Oh, there we go. It's just taking a while to name it, just a lot. So I just want to take you back to the evolution diagram because that I think will help answer your question. Okay, so we know that, so the initial ratio from the isochrons, they have model ages that are older than plume magnetism. So their model ages are, so for the peridotites, the model ages are 3.2, 3.0. So if you extend that initial ratio back. So that shows that the host rocks are that old, but that they re-equilibrated isotopically at the time of plume magnetism at 2.7. And that's why we now get an isochron that's recording the time of plume magnetism. So there's some decoupling happening. So you have the older lithosphere and you have fluids infiltrating, trapping those older inclusions. But in this process, there's isotopic re-equilibration, and then you get a beautiful nice isochron.
So Cara, can I just follow on from that? So people are still happy with the idea that during these large igneous province events, these plume events, some diamonds are being destroyed, right? And
Well,
some are being created.
certainly during my PhD, I studied in the superior craton, the mid-continent rift. There's evidence that at 1.1 GA in the southern superior craton, the mid-continent rift heated the lithosphere, and there's evidence for diamond destruction at that time. And the diamonds that we see now formed after the rift, once the lithosphere had cooled down again, re-thickened, and diamond stability had been re-promoted. So I don't know yet if there's a way to predict which one of the two scenarios it's going to be.
Okay.
We have a plume. Is it going to only destroy? Is it going to form? Is it going to do both?
And the reason I ask is not so much about diamonds, but more about the magmas that are then being supplied to the surface.
Of course, you don't study diamonds.
I know, I'm sorry. But we have lots of debates amongst ourselves here. You know, people say the Bushveld and the Ventersdorp and things like that. How much lithosphere, subcontinental lithosphere, the magmas are assimilating? If they're destroying diamonds, they must be destroying the material around them. So is that really good evidence that these magmas or melts do eat up a lot of the SCLM on their way to the surface?
I think they have to. Because certainly, well, I'm not going to go back, so it's going to take a while because I think it's too far back. But from the peridotite ages, the rhenium ages, they show that there was a lot of depletion happening in the lithosphere at the time of Ventersdorp magnetism. And so certainly it's not completely destroying it. It is assimilating parts of it, depleting parts of it, infiltrating the fluids and melts related to this, not necessarily obviously the basaltic precursors, but smaller scale fluids related to this whole plume impact, infiltrating, forming diamonds, metasomatizing other minerals in the lithosphere. So certainly there's a range of interactions that are happening. So it's not as simple as just there's a plume and now it's destroying everything.
Okay. Cool. I see Sue's raised her hand. Sue, do you want to unmute and ask your question?
Hi. Yeah, thanks, Karen. Thanks for a great talk. I'm sorry I couldn't be there in person. I wanted to ask about the, well, you mentioned in your study in Canada, you could see evidence for the destruction of the diamonds. And I'm wondering how you might constrain the size of that destruction with refertilization. And one of the reasons I asked that is certainly in the Kaapvaal project, we were able to map out an area of slow seismic velocity within the Kaapvaal craton that we've always debated about whether this was a scar from refertilization, whether, and what the age of that scar is. So any comments on how we could map the damage, say, to the older keels?
Yeah, so one way to do it would be to do pressure and temperatures on the peridotites or on inclusions or any minerals you can find. Do pressures and temperatures and determine a geotherm for the cratonic lithosphere at a certain time. So determining a paleogeotherm. And so in the case of the superior, the geotherm that we determined for at 1.1, and that is because these rocks came up at in a 1.1 kimberlite. So we knew that it was sampling the prevailing temperature conditions at 1.1. That geotherm was a lot warmer than the average cratonic lithosphere. And it also, so it intersected the convecting mantle. The geotherm for the lithosphere intersected the convecting mantle very shallow. So that means that the lithosphere was much shallower than an average cratonic lithosphere. So in that case, we think that the plume destroyed about 80 kilometers of lithospheric mantle. That was then subsequently rethickened after that, because the geotherm that's calculated for the Jurassic kimberlite at, I think it was 120 minutes, was the geotherm was a lot steeper, and it intersected the convecting mantle at around 200 kilometers, 480 kilometers. So in that case, we could see that the lithosphere was rethickened in that time. So we have two geotherms sampling the lithosphere at different times, and you can see here it's shallow, here it's thick. And this overlapped with the time of plume destruction. So doing pressures and temperatures is certainly one way, or the only way to do that.
That's really exciting to be able to see that through time. Thank you.
Yeah, and that's why kimberlites are so great, right? It's because they're sampling the lithosphere at a certain time. So you date the kimberlite, you find out the paleo conditions of the lithosphere at that time, and then seismic tells us the present day conditions. And so then, we can use both to look back in time, but then also see if that has been preserved through to the present day by looking at the seismics.
Cool, thank you, Sue. Do we have any other questions from the audience here or from the audience on Zoom? Let's have a look. Sue, we've taken you. Okay, I think we've covered everything. So thank you once again. All the commenters saying thank you, Karen. Great talk. Really appreciate it. And we look forward to seeing new data from our lab fairly soon.
Yeah, so I think with the new equipment, we could do a lot of very interesting work. And so certainly I look forward to collaborating with everyone, using the instruments and doing some exciting science.
Right. And so next week, there is no Geotalk because it's the Easter weekend and lots of people are traveling. So we take a break next week. The week after that, we have Stephanie Werner from Norway, who will be speaking about the latest research on Mars rovers, and exoplanets. So not in person, no, on Zoom. So, at least I don't think she's coming. I didn't invite. Trip to Mars in 2 weeks' time. Thanks, everyone, and we'll see you then.